Next speaker of the morning is Marcelo Fiore. He talks about stabilized profunctors and stable species of structures.
Thank you, Pino. Thank you, Alino, team, and Federico, and all others organizers for this excellent conference. What I want to talk about today is the formation of two notions that are quite well known. One is the notion of a profunctor, and the other one is that of a species of structure. And what I'm going to do throughout the talk is really to motivate and explain how we're going about this deformation, which involves some kind of stabilization. So I'm going to make all these things precise. The idea for the talk is as laid out over there. So I'm going to, as background, talk about profunctors and their functorial counterpart, which is something very well known for continuous functors. From there, I'm going to recall or introduce the notion of a generalized species of functor. These are combinatorial structures that when you see them functorially, they become so-called analytic functors. At that point, I'm going to explain the direction of the work, which is to have a theory that takes into account the notion of polynomial functor. Having done that, then we introduce really the main topics of the talk, which are these stabilized profunctors. They will correspond to a notion of a linear functor that we will see later on. And finally, based on that, we'll look at this version of species now with respect to these stabilized profunctors.
Hey Marcelo.
Yes.
It sounds like you're in a wind tunnel. Yes. Can you move the microphone away from the first?
Up or down?
I don't think.
Also, I apologize because I forgot to say that this is the joint work with Zainab Galay and Hugo Paquet, and in fact Hugo is over here somewhere. What about now? It's the same. What about now? It's the same.
That's better.
Yeah, absolutely. I'll try not to move the video. Okay, so a profunctor is from a small category A to small category B. It's a functor from small category A to presheaves over B. This is just to introduce my notation for presheaves. It will be important for us, and we will see this later on, to see them really as a generalization of the notion of binary. And it is a very known and well-known and fundamental result, really, that there is one-to-one correspondence, in fact, by categorical correspondence, with the continuous functors between presheaf categories. And the idea is to keep on analyzing this kind of situation in more and more different settings. So the structure that I'm interested on the bi-category of profunctors, I'm going to go through it now. And this is the kind of structure that I want to carry on in this new stabilized setting. So first of all, we have symmetric monoidal structure, which happens to be closed. It's given by the Cartesian product of categories. It is closed really because the category is somewhat degenerate in the sense that it has compact closed structure, and the duality is really given by taking the opposite of categories. Very importantly, for one part of the structure I'm interested in, and this will come up later on, is that we have byproducts. This is given by the coproduct of categories. And fundamentally, we have a component on the bi-category of profunctors, which associates to a category the free symmetric monoidal category only. This appeared in talks yesterday in the context of symmetric sequences. A very important example is to take the free symmetric monoidal category on a one object category, and what you will get is the sum of all the symmetric groups. This is where symmetric sequences will come later on. I will write sigma for that category. Okay. So this commoner allows us to introduce this by category of generalized species, which we did with Nicola Gambino, Martin Hanlan, and Lynn Winsker. It is the Cook-Claysley category of this commoner of three symmetric monoidal categories. So a generalized species is the profunctor from the three symmetric monoidal category on A to B. And these are called as such because when you take the example of A and B in the one object category, we recover the previously introduced notion of species by Joyal. So the category of species from 1 to 1 is nothing but set to the groupoid of that is the sum of all symmetric groups. These, as I said before, are the symmetric sequences we counted yesterday. Okay, what is the structure I'm interested in species of structure? So first, that the bicategory happens to be Cartesian closed. And the fundamental reason for which this is happening is because the three symmetric monoidal completion actually behaves like an exponentiation. So the three symmetric monoidal completion on the empty category is the one object category, and the addition of the symmetric monoidal completion on an addition is actually the algorithm. So this is a general fact. I'm not going to go into the technicalities, but I really want to look at an idea of the development of the theory I'm going to introduce. Moreover, this bicategory has the full differential calculus, and this is really coming from the byproduct structure of profunctors. And this byproduct factor, in fact, transforms into commutative bialgebra structure, and that's really what underlies the notion of differentiation. Okay. So now, in the same way that we associated a functor to a profunctor, we want to understand what happens when we do that to generalized species. Okay? And so every generalized species induces a functor between pre-shift categories, and this is like an exponential power series construction. So you think of the generalized species as the coefficients of the exponential power series, and you obtain this in categorical form really by an extension. And you see there that the analytic functor of the exponential power series associated to it is some kind of sum of the coefficients over the monomials. Now, again, if we look at the example of Joyal, when A and B are the one object category, we obtain that these are endofunctors on set of the shapes that really match exponential power series. So sum over the coefficients, and then you quotient by the group action associated to the species. Now, we are interested in characterizing the analytic functors and in an intrinsic way. And that's a theorem that André Joyal proved when A and B were 1, that is for endofunctors on set, and I extended for all endofunctors, for functors between groupoids. So when A and B are groupoids, what we happen to have is the result that the analytic functor induced are equivalently finitary and also preserving wide quasi-pools. And here the notion of quasi-pool is fundamental. Okay. So, in fact, I don't know how to prove this result for A and B categories, so that's another question. And really, for my proof to go through, I really had to restrict to groupoids. So this is a technical reason for which groupoids, at least from my point of view, seem to be much better behaved than categories for the development that follows. And so from now on, I'm going to restrict to groupoids. And let me just emphasize that all the structure that I isolated before actually actually restricts to groupoids, and so everything I was doing for categories now makes sense to restrict it to groupoids. So the category of species of structures now restricted to groupoids, it's again Cartesian closed and has this differential structure. Okay, so now what I'm interested is actually not in this exponential power series or analytic functors, but really in a theory that would also deal with polynomial constructions. And there are many motivations for doing so, from category theory and theoretical computer science. But I'm not going to say much about that. And by polynomial here, what I really mean is, in the concrete form, it has to deal with something like a power series construction. And from the extensionality point of view, there has to be some kind of functors that are finite, but also preserve not Y quasi-pool, but actually Y pools. So that's the direction we want to go. And as I said, I'm interested in also having all this structure around us before. So the main idea, this is the key of the talk, is that to pursue this theory, what I have to do really is to regard the polynomial construction actually as being analytic. So you see, every power series can be seen as an exponential power series by taking the coefficients of the power series and looking at the free action on them. So really, what we need to do is to understand or look into the actions of the species of the polynomials. So we're going to take the viewpoint and push it quite much further that the polynomial functors are really analytic functors in disguise. Okay, so to do that, we really need to look now at the sheaves of a groupoids. As I said, everything from now on is a groupoid, even if I keep on calling it A and B. And think of them as group actions. I mean, of course, more generally, groupoid actions. So here are some examples of these actions. So we have the free actions, which are the representable functors. If we sum actions, we get new actions. This, if you start with the free ones, to remain free ones. And crucially, we create new ones by taking quotients. So if you take any subgroup of automorphism of an object of your groupoid, actually you can quotient a representable. And essentially, this is the only way in which we can actually create actions. So first of all, every presheaf is of the form a sum of a quotient of representables. This is the usual theorem that we know, that every presheaf is a colimit of representables, but now it's actually with the example of groupoids. And it's interesting to see where these quotients come from. They actually come from the elements that are induced by the elements of the presheafs by looking at the stabilizers. So the stabilizer of an element X of a presheaf X, say over AI, is nothing but all the automorphisms that fix the element. So if we're going to analyze the presheafs of a groupoids and want to distinguish between the free ones and the arbitrary ones, we really need to look into this kind of stabilizers. This kind of idea we really took from a paper from 1989 from Paul Taylor, who started this analysis. We're pushing it in a different direction. Okay. Now, importantly for us, for every point or element of a presheaf, the class of all element of the presheaf set of A, the set of all stabilizers of all the poles is actually closed under computation. So these are subgroups of automorphisms, and so we're going to be interested in families of subgroups of automorphisms that are closed under conjugation. This closure under conjugation is really motivated by the fact that we are interested in capturing in abstract form the notion of stabilizer. So that leads me to this notion of a kit, which is the fundamental piece of structure for us. So a kit on a groupoid A is an assignment that to every object of A, associate a family of subgroups. This family of subgroups need to be closed under conjugation. The idea here is that this family of subgroup is telling you the subgroups that you are interested in being in a stabilizer of. Okay. And of course we have a lot of examples because every pre-sheaf will give you such a class by taking all the stabilizers of the elements of the pre-sheaf.
What do you mean by stable under conjugation? You fix the little a, or you can also...
You fix the little a.
Oh, okay.
Yes. Well, actually, no, it's conjugation arbitrary. You don't fix the little a. So if I have A here, B here, have a group here, and an isomorphism between them, this group, when I conjugate, it appears in the kit here. That's it.
Fine, normal subgroup.
Well, yes. It is not the notion of normal subgroup for group is not the same as for the group, so you don't have to call it like that. Okay, and now these group poles with these kits allow me to cut down the pre-sheaves. And I am cutting down to those that are stabilized. Okay. So pre-sheaf is in the S of AA, precisely when all the stabilizers, so all the elements of the pre-sheaf happen to belong to my kit. Okay. So what these kits are doing is controlling the kind of actions that you can perform on any element of the pre-sheaf or the action. So here are the way in which one can actually specify the free actions. If I said essentially that my kit contains of the trivial subgroups, then when I look at the stabilized pre-sheaf, I only get the free ones, which in this case are nothing but the sums of representatives. And so, in fact, we have the following representation theorem. S of A is in fact the whole product completion of all the quotients of representative. When you restrict those quotients to living in the kit. Now what I want to do is to look at the bi-category, which I'm going to build up, of group poles with their kits, and such that it supports all the structure I talked about. And in particular, it should support a duality. So we should be able to define a duality on a group pole and its kit, so that now we have the duality of the bi-category of profunctors together with the new duality of these kits. Now the question is where this duality for kits should come, and the point of view that I'm taking, it should come from a Boolean algebra of kits. Okay, so what's really going on here is that the compact closed structure of profunctors, we're going to have a Boolean algebra structure on kits, and we are going to put them together to build a new duality on a bigger structure. So where is this Boolean algebra coming from? So I'm going to introduce, it can be introduced from many points of view, and I'm going to introduce it from a concrete one. And in fact, that comes from a Valois connection induced by orthogonality. Okay. So let me do this for a group. So two subgroups of a group are said to be orthogonal when they have a trivial intersection. Okay. And once you have this notion of orthogonality, you can consider all the groups that are orthogonal to a fixed set of groups, say in a kit, and now you consider the double closure of this construction, and that's where our Boolean algebra is going to come from. Okay? So for a kit A, I can take its orthogonal to consist of all the groups that are orthogonal in the sense that have trivial intersection to every group in the kit. So it's some kind of notion of disjointness or complement inside the subgroup structure. Okay? And then my Boolean algebra is going to come from looking at all the kits that are double orthogonally closed. So in fact, this condition imposes very strong closure properties. So a kit should not be empty. All kits are necessarily double closed. they're closed under filter unions, and they have, in fact, they have very strong extensionality property. So you can actually describe the whole kit by looking at all the elements in the groups that appear. And so I'm going to introduce this construction that alpha, this notation, that alpha kind of belongs to the kit precisely when it appears in one group in the kit. Okay. In fact, there is a universal categorical way to describe this, but I don't have the time to show it to you right now. So now we are interested in defining a notion of profunctor between these groups with kits. It has to have at least two properties. That if I have a kit to be the subkit of another one, then it becomes, this can be mimicked by an homomorphism, and it has to preserve the duality. So what you come up with is the following definition. It says that a profunctor is stabilized whenever actually it's stable by acting on the left and on the right. The following property has to be fulfilled, is that if alpha is kind of a proof of A, then beta should be a proof of B, but also the contrapositive. If beta appears in the negation of the kit B, then alpha should appear in the negation of the kit A. And in fact, this has a categorical reason for being the case, which is that the profunctor now seems that the functor actually restricts both to the stable presheaves in the kits, but also in the algebras. Okay. So now we have a notion of stabilized profunctor, and in fact, the theorem is that we can characterize them extensionally as functors between the associated categories of stabilized presheaf, and these are functors that we call linear, which by definition are left and right local adjoints. And this category, this new bicategory of stabilized profunctor, now exactly has the structure as before. But in fact, this structure is more refined because it's not compact closed anymore, but star autonomous. So, in a sense, it's more sophisticated. And of course, because we have a symmetric algebra comonal on this space, the definition of which is quite non-trivial, we can define stable species. So the stable species is now, again, species as before, but in a way that the kits are involved. And now we can ask which kind of functors they correspond to. And they correspond to functors that we call stable, and these are essentially polynomial. So they are finally, they preserve epimorphisms, and they are actually local right adjoints. Okay. So because of the previous structure that we have, now this bicategory of stable species between these Boolean kits is Cartesian closed, and in fact also has a differential calculus. In fact, all this structure is really inherited from the bicategory of species. And what's really going on here is that we are in a sense doing a bicategorical gluing construction. However, this notion is still to be defined in the bicategorical setting, and that's the kind of direction we are going for. Thank you very much.
Other questions? Oh.
Thank you. I'm trying to understand kits better. Is there I mean, you define kits in the context of groupoids.
Yes.
Is there an extension of the concept to categories?
So I can say two things. This notion of Boolean algebra that I generate from a kit, I can actually associate it to any algebraic theory. So that's not only restricted to groupoids now. So, but what the problem is this one. I cannot generalize these two categories, and I tell you exactly what the problem is. Yes, so you want to define, as I said, the notion of a profunctor between these groups with kits that has at least these properties, because you want to have the duality built in. Okay. And of course they have to compose. And the problem is that to make them compose, I really need the groupoid structures so that this property is preserved. So I don't know how to do it for categories. Yes, I don't know. I tried. I don't know. Like it might be done a bit more generally with other things like not groupoids, like inverse semi-groups, but I also don't know.
Thank you for your talk. I've also tried to understand kits, but in the other direction maybe. Is there a way to think of what they're analogous to in relations?
In relation, they don't exist, so you cannot. Because a kit, as you see, what's happening here is this another way to see. You have your groupoid. You can think of it as a generalized set. So if the objects are the points of the set, but now these points have an internal symmetry. This internal symmetry is actually generating a Boolean algebra. And a kit is a way to associate to every point of your groupoid an element of the Boolean algebra that is intrinsic to the symmetry of the group. And in relations, you have relations between sets, and the Boolean algebra is trivial, so the kit is trivial, so you cannot see the structure there.
When I was doing this a long time ago, I wanted to smuggle some finite group theory into this subject, but I only got weak products of permutation groups. Have you found any more interesting group theory?
So, not really. So, what I've done is try to understand these Boolean algebras associated to these groupoids, and it's not clear actually. In fact, they're super hard to calculate. I have tried to see if these people have looked at it in group theory, have looked at this, and none of the group theories I've talked with, they tell me that I've seen anything like this. Some tell me it's not interesting because this is not, this Boolean algebra is not interesting from the point when you quotient a group, so I don't know. It's new concept.
I wonder if there is a topological version of your kits, because in the one object case, it's more or less a filter of subgroups, so which generates topology. And
yes. So
in the groupoid case, you get some kind of Descartes groupoid or something like that.
I don't know. So of course I did everything set based, but I can be V enriched.
No, but I mean that the data of a kit
Yes.
should be equivalent to a topology on the groupoid.
Okay. So I don't know. Maybe if I explain you in categorical form what the Boolean algebra is, you can see it. Because the Boolean algebra is obtained by looking. So you start with your group. Let's do it for a group. So you start with your group. You take the algebraic lattices, of all the subgroups. Okay, now we close them on the conjugation because we want that. And now you take a free frame on that, and now you Booleanize it. So that's, and then a kit is a point in this Boolean algebra. So maybe that gives a route towards that direction. I have not tried that. Thank you very much for the suggestion.
There was another question.
Yes, thanks again for your talk. In one of the last slides, you mentioned that the functors between the stabilized species were the were preserving ones.
Yes.
Yeah. So what made the quasi disappear here?
The stabilization. So you see when you are I mean, this profunctor have to have this very strong property, and so that it's forcing everything to become in a free way, free with respect to the kit structure.
So this is a freeness property.
Yes, it's a way you control the kind of actions that you can perform. Okay, and when your kit is trivial, you are controlling it so much that you force the action to be free.
But it's not always true.
Not always trivial. But then you are, yes. But then you are restricted not to all pre-shift, to the ones that are stabilized. So that's the intuition. Now, you're not working on arbitrary pre-shift, you're working on the stabilized ones. So for those, you are behaving in the proper way, freely.
Okay, thank you.
I allowed a few more minutes because there were several interruptions this morning. Let's thank Marcelo again. And we resume